Hi, my name is Tim Hosgood and I'm a PhD student at the University of Aix-Marseille, currently finishing a year-long position as part of the Simp app team at the University of Montpellier. And this video, which is made for the Junior Mathematician Research Archive, aims to explain the work of my PhD thesis, which was split into two papers, preprints of which can be found on the archive under the titles Simplicial Chern-Weil Theory for Coherent Analytic Sheaves, Parts 1 and 2. For this video though, I'm going to be working from my thesis, just because then everything is in one place instead of two. The intended audience for this talk or this video is really anybody who cares about either Chern-Weil theory or coherent analytic sheaves, because it's kind of split into these two topics separately. So let's start with some historical context. In 1980, H.I. Green wrote his thesis on the subject of Chern classes of coherent sheaves on complex analytic manifolds. The work inside was never published, but an exposition was written by Toledo and Tong, whose work on twisting cochains with O'Brien, who was one of Green's supervisors, formed the backbone of Green's thesis, alongside Dupont's fibre integration. The construction, which gives classes in H2k of x of omega x, truncated below in degree k, agrees with the classical construction by Atiyah-Hirzebruch in H2k x of z. Then, nearly 30 years later, in Griveau's thesis, this construction was mentioned as one that should fit into an axiomatization of Chern classes on compact complex analytic manifolds that ensures uniqueness, but the details still hadn't quite been worked out at this point. Finally, for now at least, but hopefully not forever, this year we figured out how to fit all these pieces together by showing that Green's construction is a specific and somehow prototypical example of a more abstract construction. For those who work with Chern classes in algebraic geometry, this might all seem rather odd. Indeed, in the complex algebraic world, the construction of Chern classes has been really well understood ever since work by Grothendieck, amongst others. But there are two problems with using Chern-Weil theory in the complex analytic world. Firstly, coherent sheaves often do not admit global resolutions by locally free sheaves, and in fact Voisin gives a whole family of counterexamples, or examples of this statement. And secondly, global holomorphic connections on holomorphic vector bundles very rarely exist. This means that the classical method, which is to take a locally free resolution of your coherent sheaf, take connections on each vector bundle, use Chern-Weil on the curvature of each connection, and then take some alternating product, breaks down in two ways. Luckily though, both of these problems are sort of the same type of problem. They result from the non-existence of a global object, even though local objects always exist. That is, we always have local resolutions of coherent analytic sheaves by locally free sheaves, and local holomorphic connections always exist on holomorphic vector bundles. This is where simplicial methods become incredibly powerful. We actually can obtain some global object if we slightly weaken what we mean by global object. But then, using Dupont's so-called fibre integration, we can actually turn these quasi-global objects back into strictly global ones. So here's the plan. First, we're going to figure out how to do Chern-Weil theory for vector bundles. This means we will be looking at so-called simplicial connections. Then, we will try to understand how coherent analytic sheaves are resolved by so-called vector bundles on the nerve, which is somehow the good notion of simplicial vector bundles, even though they're really not simplicial vector bundles. And finally, we want to prove that everything fits together well homotopically, that is, on the level of infinity 1 categories, and we want to show that we recover all of the classical calculations. So let's start with some maths. One fundamental construction is that of the check nerve of a cover, which is a simplicial space, that is a collection of spaces, one for each natural number, along with face and degeneracy maps between them. This is something that we'll be using a lot in what follows, and we tend to think of it as a sort of exploded version of our space. For what follows, we're going to fix some paracompact complex analytic manifold X with a finite Stein cover, U, and we're going to take some locally free sheaf E, which we can also think of as a holomorphic vector bundle, and generally we will use locally free sheaf and vector bundle somewhat interchangeably. And we'll take E to be of rank R. For simplicity, we can assume that R cover U trivializes E, so that we have these transition maps, M alpha beta, which can be realized if we take some local connections S alpha as R by R matrices. Now we consider the Atiyah exact sequence of OX modules, which contains the first jet bundle, and its corresponding X'd class, which is called the Atiyah class of our locally free sheaf. It is a nice classical fact that the trace of this class somehow is the same as the first Chern class. This is a result found in Huybrechts, for example. But it's also the case that this class describes the obstruction towards E admitting a global holomorphic connection. Indeed, a holomorphic connection is exactly the data of a splitting of this short exact sequence. So we already see how Chern-Weil theory breaks down, because the moment our vector bundle has a non-trivial first Chern class, it cannot admit a global holomorphic connection, so we can't take the curvature and evaluate some invariant polynomial on it. That is, the moment there is a first Chern class worth calculating, we can't calculate it with Chern-Weil theory. But we can be a bit more explicit about this Atiyah class. If we assume that we have local holomorphic connections, which is always the case if, for example, we have a basis of local sections, then we can actually write down the check cocycle in terms of transition functions of E, and the trace of this is de Rham closed, and by definition as a check cocycle is also check closed, which means that it gives us a closed class in the total complex of the check de Rham bicomplex. Since we're working in a nice enough setting, this means that we get a class in de Rham cohomology, or even truncated de Rham cohomology. Before introducing any of the formalism of simplicial constructions, that is, these sheaves on the nerve, we can think a bit more about the computational problem. Can we lift the kth Atiyah class, which is just the wedge product of k copies of the Atiyah class, to give a closed element in the check de Rham total complex when k is greater than 1? The answer is yes. The second Atiyah class is already check closed, but it's not de Rham closed. However, if we calculate its image under the de Rham differential and consider all possible polynomials in one formal variable and their images under the check differential, and work with these polynomials in two formal variables that are quotiented out by cyclic permutation, under which the trace is invariant, we can just do a brute force equating the coefficients and find a check 1 cocycle of 3 forms such that we get a closed element in the total complex. We can do the exact same process, but twice, to compute the analogous correction terms for the third Atiyah class, but we already see that things are starting to get a bit messy. Indeed, by the time we reach the fourth Atiyah class, the polynomials are already way too large to be able to spot a pattern by just looking at them. So we see that we need a slightly fancier approach if we want any hope of getting classes in de Rham cohomology for further Atiyah classes. So this is where we now turn to the simplicial construction. First, we need to know what the good notion of a simplicial vector bundle, or more generally a simplicial sheaf, is. This is something that was described by Green, but hasn't really seen much use since. In fact, these objects are interesting enough in their own right that they deserve a much more thorough treatment, since they can actually be realized by an abstract, but concrete, construction of Bergner, as lax homotopy limits of model categories. But that's another story for another time. Here we'll just give the definition, as well as a kind of vague motivation. A sheaf on the nerve is a collection of sheaves, indexed by the natural numbers, with each EP being a sheaf on the pth level of the check nerve, such that, for any morphism in the abstract simplex category, we get covariantly a functorial morphism of sheaves. Here, functorial means that it respects composition, and when we say sheaves, we can just mean topological sheaves, or, what we're more interested in, sheaves of OX modules. But then, really, each EP will actually be a sheaf of OXP modules. These sheaves on the nerve have been called simplicial sheaves, but this is kind of a misleading name, since they're not really simplicial objects in some category of sheaves, because as we've said, each EP is a sheaf of OXP modules, not some global OX modules. And these objects don't even look simplicial. If anything, they would be cosimplicial, because they're covariant with respect to the abstract syntax category. So we're just going to stick to saying sheaves on the nerve, even if it is a bit long-winded. An important and even prototypical example of a sheaf on the nerve that really motivates this definition is given by pulling back a sheaf on X along the map from the check nerve to X. So now we can state our current goal a bit more explicitly. If we take a holomorphic vector bundle with a non-trivial Chern class, so one that does not admit a global holomorphic connection, and we pull it back to the nerve to get a vector bundle on the nerve, is there some good notion of simplicial connection, such that A, these things always exist, and B, we can take their curvatures, evaluate them under invariant polynomials, and get some class in de Rham cohomology? The answer to this question is, luckily, yes, and this was exactly one of the two main things that Green showed in his thesis, with the other being the existence of very nice simplicial resolutions of coherent sheaves, which we'll come to later. But Green's construction, all perfectly functional, does not really give any indication as to why this method works, nor how we could generalize it to give a general definition of a simplicial connection. That's the aim of this chapter of my thesis. Although there are a lot of very technical and seemingly uninviting proofs, the main motivation, which can be found in Green's thesis, is really quite simple and quite beautiful. It goes as follows. Locally, we always have holomorphic connections, say nabla alpha on each U alpha. We know that we cannot glue them together if we have a non-trivial first Chern class. That is, on an intersection U alpha beta, it will not be the case that nabla alpha and nabla beta agree. But what we can do then is just take both of them in a barycentric average, if you will. That is, we consider lambda minus 1 nabla alpha plus lambda nabla beta for lambda in 0, 1, the closed interval. When lambda is equal to 0, we recover nabla alpha, and when lambda is equal to 1, we recover nabla beta. And for any other value of lambda, we get some weighted average of the two. So what we've constructed on double intersections is a connection parametrized by 0, 1, that is, by the 1 simplex. And we can do the same on triple intersections. We take some linear combination of nabla alpha, nabla beta, and nabla gamma, and we parameterize by the 2 simplex. We can think of this as a triangle, and then any point on the boundary corresponds to forgetting one of the local connections, and any vertex corresponds to forgetting 2 of them, and just remembering 1. Proceeding like this, we can build, on each level of the Czech nerve, that is on each P intersection, a connection that is parametrized by the P simplex. Using this construction, we can explicitly calculate the curvature, which gives us what we call the first simplicial Atiyah class, since we can show that, working over U alpha 0 on any P intersection U alpha 0 to alpha P, it contains the Czech cocycle representing the Atiyah class that we've already calculated. If we then take the trace of this, we get what's called a simplicial differential form. That is, a bunch of differential forms on the simplex times the Czech nerve that satisfy some kind of gluing condition resembling that of the fat geometric realization. But this is where Dupont's fibre integration comes into play. There's a quasi-isomorphism between the simplicial de Rham complex and the usual de Rham complex. So we can go through and write down what we get when we follow this whole procedure, actually calculating these integrals, and we see that the fibre integral of the trace of the first simplicial Atiyah class is exactly the trace of the first Atiyah class. In fact, the same is true for the second Atiyah class as well, and for the third, even though now the equality only holds in cohomology and not directly on the level of cocycles. More generally, as one might hope, we can show that the result is true for all the Atiyah classes. Everything we've said above is really just a nice way of explaining in more detail what Green did in his thesis, but we said we were going to do something a bit more general and give abstract definitions for simplicial connections, so let's do that now. We already have a vague idea of what a simplicial connection should be. It should be a bunch of connections, each one on the pth level of the Czech nerve times the P simplex. But we'll probably need to be a little bit more strict with what we call a simplicial connection, since this object we're describing seems pretty general. Indeed, let's think about what we need the connection to satisfy. First, we want to get a simplicial differential form when we take the trace of the curvature, so that we can apply Dupont's fibre integration. This means that the simplicial connection should satisfy some sort of compatibility between different simplicial levels, akin to the equation satisfied by simplicial differential forms. This can be guaranteed by asking for a certain condition on what we call the comparison maps. That is, we say that such a collection of connections is a simplicial connection if the comparison maps are true morphisms, which simply means that they commute with the connections. Again, this seemingly arbitrary condition is actually exactly what we need to ensure that the resulting differential forms will satisfy the simplicial condition needed to be able to apply Dupont's fibre integration quasi-isomorphism. Next, we need to worry about the fact that we have a bunch of connections, and so, when we take their curvatures and evaluate them under some invariant polynomials, such as the trace after taking a wedge product, there is no reason a priori that we will get the same result at each simplicial level. That is, we might get a bunch of different characteristic classes. We can solve this problem by asking for the comparison maps to be admissible, which is a purely formal property motivated by the following simple, but entirely arbitrary seeming at this point, definition. Given pairs V, phi, of finite dimensional vector spaces and endomorphisms on those spaces, we say that a morphism F from V phi to W psi, which is assumed a priori to commute with the endomorphisms, is admissible if there exist subbundles V1 in V and W1 in W, such that firstly F restricts to a morphism from V1 to W1, And secondly, further descends to an isomorphism on the quotients v quotient v1 to w quotient w1. In some sense, which we can actually make much more precise, a morphism is admissible if it is an isomorphism away from some flat subbundles, where we won't define here how we can think of these subbundles as flat, but we can. If all this sounds a bit hand-wavy, then it's probably best to go and read this in some more detail, because I don't want to get lost in all of the technicalities here, and there really isn't anything that fancy going on. I promise that this idea of admissibility of a simplicial connection is exactly the condition needed to ensure that the characteristic classes are well defined, is all that's going on behind the scenes. Finally, we might worry about our initial data. That is, if we started off with some different choices of local sections and local connections, then would we still end up with the same characteristic classes? The answer is a priori no, so we need to ask for another condition. We say that a set of admissible simplicial connections is a compatible family if the difference between any two of them is itself an admissible endomorphism-valued simplicial one form. We haven't defined here what exactly such an object is, but it is written down in full detail, and again, the idea is exactly the same as above. It's some kind of endomorphism-valued simplicial form that's isomorphic between different simplicial levels if you quotient out by some subpart that is, in some sense, flat. Note also that we haven't really said what an invariant polynomial is, and we actually need to modify the classical definition slightly, because we need a bunch of invariant polynomials, one for each simplicial level. Again, there are some small technical conditions that we impose on them, but they aren't very restrictive, and all the things that you would hope to be invariant polynomials, such as the trace precomposed with the wedge product or the trace precomposed with composition, are indeed generalized invariant polynomials. The last, very reassuring result of this section is the following. Green's barycentric connection, whose construction we described earlier, is indeed an admissible simplicial connection. In fact, an even stronger result holds. Given a sufficiently nice complex of vector bundles on the nerve, where here sufficiently nice will be explained in a bit when we talk about Green's resolution, we can endow each vector bundle on the nerve with an admissible simplicial connection, and the family of all such connections arising from different initial data is a compatible family. That is, if we have a sufficiently nice complex of vector bundles on the nerve, then we can do Chern-Weil theory to calculate Chern classes of each of them. To prove this, we introduced the idea of a simplicial connection being generated in degree zero, which very loosely, but also very accurately, means looking exactly like Green's barycentric connection. The second piece of the construction that we've been skirting around is how to bring this construction up to the level of coherent sheaves, that is, how to get around the problem of coherent analytic sheaves not having global resolutions by locally free sheaves. This is something else that Green solved in his thesis, by using the twisting cochains of Toledo and Tong, which are very linked to, and in fact specific examples of, but not quite the same as, the twisting complexes of Bondel and Kapranov, to prove the following result. Any coherent analytic sheaf, when pulled back to the nerve, has a resolution by vector bundles on the nerve, and these vector bundles satisfy some nice properties. What exactly are these nice properties? Well, one way of saying it is the following. They're exactly the nice properties that we said we would need to prove our previous theorem, and being able to endow a complex of vector bundles on the nerve with admissible simplicial connections in a compatible family kind of way. Another way of describing them is the following. On any intersection u alpha beta, these vector bundles on the nerve look like the part over u alpha, direct summed with something that is homotopically trivial. Formally speaking, we mean something that is elementary, that is a direct sum of possibly shifted identity morphisms. This implies, in particular, that the cophase maps are injections, and that the codegeneracy maps are surjections. Recalling what we said some 5 or 10 minutes ago, although sheaves on the nerve are not cosimplicial objects in some category of sheaves, when they satisfy this property, they look a lot closer to being such things, since they have injective cophase maps and surjective codegeneracy maps, which is something that cosimplicial objects always have. Twisting cochains, and indeed Green's resolution, come with a lot of very long-winded, heavy matrix calculations, so we really won't talk about them here, but there are some nice details written down that show how Green's resolution can be understood as a sort of semi-strictification of twisting cochains. We also go through the example given in Green's thesis in a bit more detail, showing how you can calculate the first Chern class of a skyscraper sheaf using all the formalisms that we've developed. And this method of Green is so nice because you actually end up with explicit check de Rham representatives for the cohomology class. whereas a calculation of the Chern class using, say, short exact sequences and the Whitney sum formula will only give you the cohomology class itself. So what's left to do? We've discussed Green's construction and shown how it fits into a more general, more abstract framework via admissible simplicial connections, potentially generated in degree 0. And we've also shown that it agrees with this manual lifting that you can do by equating coefficients of polynomial and cyclic permutative variables. What more could we hope for? Well, up until now, everything we've said has been nice, but we haven't really made things much more useful. We've just given everything a much fancier and much longer name. It would be much better if we could actually say things in the language of category theory, and indeed in the language of infinity 1 categories. This would tell us that the construction is somehow a good one, in that it respects the inherent structures between all these objects. It turns out that there are some technical difficulties with even deciding what exactly a complex of coherent analytic sheaves should be, but we can get around this somehow, and end up with the following result. There is an equivalence of infinity 1 categories between complexes of coherent analytic sheaves and the homotomy colimit, over refinements of covers, of Green complexes, which are exactly these complexes of vector bundles on the nerve arising from Green's resolution, that is, those that satisfy this injective cophase surjective codegeneracy property, amongst others. As a bonus fact, since X is assumed to be paracompact, for any complex of coherent analytic sheaves, this homotomy colimit will be finite. That is, we can actually do calculations and write down resolutions. All of what we discussed above amounts to a proof then that Simplicial Chern-Weil theory works on Green complexes, and so this equivalence tells us that Simplicial Chern-Weil theory also works on complexes of coherent analytic sheaves. And this is exactly what we started out wanting to show.